We started, so it's a pleasure to be back to computational PDEs. It's been a while. A lot of statistics going on. So it's my pleasure to introduce Professor John Trevelyan. How many of you seen John pre-2018?
Seen him what?
He was in the department about 7 years back.
Or 9.
Oh, 9 years. Yeah, you might have seen it. So he spent his last sabbatical here and liked it, and then looks like they've done some decent job here. So he's decided to come back here for another sabbatical. Yeah. So John is an engineer who likes mathematicians. So then he doesn't criticize mathematicians, and then he takes information from certain mathematicians, and then he enriches it. In particular, he works on two important methods for simulating PDEs. These are called finite element methods and boundary element methods. Yeah. So his focus recently has been on boundary element methods. He has also back into finite elements.
Sometimes.
The key idea is that the standard approaches work well, but it is computationally expensive for a large class problem. So what John tries to do in general is to kind of use some kind of a different type of basis functions so that it enriches the methods, and that's what he's going to talk about.
Thank you, Ganesh. I'm not sure I need to give my introduction now. It's a great pleasure to be back in Mainz. Like Ganesh was saying, I was here several years ago. It doesn't seem like 9 years ago, but here we are. You did do a great job of selling the place. The geography helps as well. The views are to die for. I am an engineer. I do like mathematicians. Some of the things I will say, if you're a purist mathematician, you may start to set a shiver that starts there and ends up here somewhere. So we take a little bit more of a relaxed view of mathematical rigor. And we aim to find computational methods that work well. If they're better than the unenriched methods, then that's good for me. So I'm from Durham University. Durham is this little village up here. Well, it's a city. It's called a city because it has a cathedral. That's the definition of the word city in the old English way of dealing with things. Scotland, the Scottish border is right about there, so I can be in Scotland in about 90 minutes drive. It's got this fabulous cathedral here, which is one of the, if not the best building in the UK. It's very close. It's a wonderful building. Some of you may have even been to Durham with the old series of AMS conferences and meetings there as well. There's a little link as well to this group here. If you actually go into that cathedral, you will see a plaque there. And this plaque, I'm sorry that the resolution hasn't survived quite a lot of changes of formatting of the image, but it celebrates this guy called John Washington. Washington in this county. Washington is a little village kind of in between those two blocks. Washington in this county, prior to this cathedral church, 1416 to 1446, whose family has won an everlasting name in lands to him unknown. So he was one of the ancestors of George. This came from very close by. He was a prior in that building right there. Anyway, what I'm going to talk about this afternoon, let's just have some introductory comments on what I mean by enrichment. This is all about what are the basic ideas of that. And then I have three examples of different numerical methods which have been enriched in one way or another. And in fact, it's quite nice because they're all enriched with slightly different philosophies, different ways of developing those functions that we're enriching. So there's some boundary element stuff, there's some finite element stuff, there's fraction mechanics. In fact, the fraction mechanics is just an overview. In fact, I'm not going to go any further than I did this when I was here 9 years ago, just to give you a flavour of the sort of thing we can do. And Ganesh has asked me to give another talk on November 14th where I can get into a bit more detail about that. And his advice was go with the fraction on the 14th. So that's what I've done. We look at some solutions to the heat equation in finite elements with various different enrichments. We'll finish up with one which I guess is our best known work, which is wave scattering. So if you are not familiar with BEM, and I normally anticipate most of the, in spite of the fact it's been my life's work, Most of the groups I talked to, there's half the people at least have not heard of it, or not come across it fully. Anyway, just I suppose this gives you the immediate eyeball difference between finite elements and boundary elements. You're just discretizing the boundary. How does it know where the volume is? Well, it's all done by taking the governing PD and casting it into an equivalent integral equation, a boundary integral equation, which leads you to a boundary-only formulation. Accuracy is very nice, and I guess I could say part of that is the fact that every one of these little elements involves an assumption that you're making. Maybe the displacement or whatever is quadratic over that little linear perhaps. We're not making those assumptions here. The assumptions here are the Green's function, the function that defines the PD in that. So there's good stories about accuracy, good stories about data preparation, flexibility, remeshing, and all those things. Downside is that, I'm not going to say it's entirely limited to problems for which a fundamental solution is available, but it's limited really in application. People do look at nonlinear problems with BEM. It's a bit clunky, and I would say probably not the right applications for BEM, in my view. Anyway, that's a very quick overview of the BEM. And, well, whether you're using FEM or BEM, you'll be familiar with statements like this, where we take our element, in this case it's an 8-noded quadrilateral, and some sort of parent space, psi eta with a -1 to 1. And we're all very used to setting up an expansion like this, which uses traditional shape functions. So our capital N's are shape functions. In this case, they would be quadratic. You can see the branching polynomials and so on. Very, very widely used for many decades, and we've all achieved a lot of comfort with them. But sometimes it's not the best solution. The reason is that sometimes it leads to a requirement for, well, one of the reasons why it may not be the best solution is the requirement for a very, very dense discretization. And one way of looking at that is looking at wave scattering problems. And here we have this rather odd-looking shape, and this is being impinged by a wave that's coming along from the lower left corner. And we can see there's various perturbations to the wave field here. Well, that's not difficult to model with those elements. If we increase the frequency, we're into what I might call medium frequency scattering, and it gets a bit more complex. And if you go to a larger wave number, you get into some really complicated wave fields, even on what is otherwise quite a simple problem. Now, one of the issues here, if I can find a piece of chalk, is if you're trying to resolve a sine wave, if you're going to do it accurately, the normal rule of thumb is you need to sample at 8 to 10, if you read different people, locations per wavelength. So the typical rule of thumb might be to say, discretize that with 10 nodes per wavelength. And here's our wavelength here. You can see that we probably need hundreds of thousands of nodes if you're just going to analyze that problem.
Are those interference patterns, or is that numerical artifact?
No, that's the interference pattern.
Yeah, cool.
So if I was going to, let's have a little sort of thought experiment. We're going to analyze the acoustics of this room with boundary element. If we're going to do it at middle C on the musical scale, that's the element we would need. So we place these all over all surfaces, all tables, us, whatever. If we're going to go take that up to 1 kilohertz, we're going to get elements like this. Still kind of manageable. We could probably do that. If we're going to go up to the audible limit of humans, 20 kilohertz, it was here earlier. So this is the one that we would need. So you start to see the scale of the problem. And it's not the sort of thing that you can get away with large, structural mechanics stress analysis. You can get away with large elements way off in the far field where you're not interested, as long as you have a refined mesh close by where you are interested. I'll do that in a few seconds. So the idea then is to find the spacer functions as better properties for the problem at hand. In other words, you might call it an operator-specific basis that you're using. So these have been around for a long time. Many of you have seen Treft's methods, where your basis is taken from solutions to the PDE. Method of fundamental solutions. This university's department has a strong, long proud history in MFS. It goes back to Caprazzi in the 1960s. It's a Treft's method. Bensley in 1974 predated XFEM, extended finite element method, by 25 years. Nice paper there, had local enrichment around crack tips. And more recently, Tom Hughes, isogeometric methods. Well, I suppose it's arguable as whether that's non-polynomial or not, but anyway, I put it in there as it's not standard approximations. So it's been around for a long time. What I'm going to do today is focus on methods like this. In fact, I'm going to go through them quite quickly because, to me, these methods all have essentially the same. They're essentially the same methods by different names with minor differences. So different flavors of the same idea. You can see the sort of era it dates from, mid-90s to 2000s, and then that's spawned a lot of research since then. So here's my idea for enrichment. The idea is, if we're trying to capture a shape, we can either do that geometrically with a zillion really rudimentary, crude cuboidal elements, or we could do it with a small number of crafted, carefully designed elements, and you end up with the same geometric solution. I like the pictures. So I mentioned a moment ago that these three different applications we're going to be looking at, the enrichment is drawn from a different way of looking at it, different ideas behind it. So when we're going to look at the wave enrichment, wave scattering, we'll be using plane waves or Bessel functions or a combination of the two. And these are functions that are complete for the PDE. In other words, you can take any Helmholtz, any solution to Helmholtz equation and express that as a linear combination of plane waves. As long as you have enough of them, you won't need a lot of them. But we know that they're complete for that PDE. Alternatively, because I'm interested in enriching these cases where I need a fine mesh very locally, because things are happening, I've got very steep gradients in my solution in that location. In which case you might be wanting to take some sort of local asymptotic behavior that could be derived from some eigenvalue representation of what's going on in the form. So XFEM, the extended finite element method, is really drawn from that because we know the analytical asymptotic behavior of displacement into a crack. And this is the one where maybe that shiver will start to go up your spine as mathematicians, because it could be just anything else that we have reason to believe will be better than the other approximations. And some of the finite element stuff I'm going to show you will be based on that. So that's much more an engineering perspective than any sort of mathematical reason for choosing those enrichment functions. So let's start out with the fraction mechanics and straight in with the boundary integral equations. This is what the BEM is based on. So we integrate the integrals are over the boundary gamma to the domain. Our unknowns are the displacement. One of the terms out here contains a displacement at a point P. There's a displacement with the variable integration here, so this is a displacement around the boundary, and here's a traction around the boundary. So there's lowercase u's and t's are unknowns. And sitting inside the integrals also we have our Green's functions or fundamental solutions, the kernel. I've heard people talk about kernel-based methods. So those are our fundamental solutions. Those are known for any locations of P and Q. And let's not worry about this out here, it's just something which arises from the singular, the strongly singular integral. So in the collocation form, we're going to take our point P, let's take our point P and put it on our node number 1, we'll place a force there. We can then compute, if we know where P is, we can compute these T's and these U's, and this ends up giving you a matrix that we can solve. I can solve my problem, I can find the displacements and tractions incidentally at the same time to the same polynomial degree. You could use a Galerkian method if you wish. Many people do, most mathematicians do, because they can prove things about the convergence and error. Most engineers, I think, tend to use collocation because it's faster and it works. So that yields a square system. But don't worry too much about this. I mean, the main thing is that we've got our displacement and traction in here. And conventionally, we would take a polynomial, Lagrange polynomial space here, but we could choose something else. So what are we going to choose? So we could turn to our asymptotic behavior of the displacement. So this is conventionally written in polar coordinates r theta around the crack tip. And so these are well known. These go back to Williams 1950 something, I can't remember. So, thank you. And what you can see here is behavior of displacement in x and y as a function of r and theta. The kappa is a function of Poisson's ratio, shear modulus in here. There are their analytical expressions. They go with the square root of r, which in itself is a fairly benign function, but when you start to differentiate that to get your strains, to get your stresses, you're differentiating r to the half, you get an r to the minus a half. As r goes to 0 into the crack tip, that blows up to give you a singularity. So that has caused numerical models some angst over the early years of modeling crack problems. The K1 and K2 are key parameters. These are stress intensity factors that fall. And key parameters for engineers are understanding the stability of cracks in their current state, but also understanding things like fatigue, crack growth rates, and life predictions. So very, very important to get those right. You'll also notice that as r goes to 0, the displacement goes to 0. So if I were to pull something with a crack in, the crack tip could very well have some sort of displacement associated with it, depending on the geometry and where I apply my loads and what my boundary conditions are. So the rigid body, this only gives you the sort of local perturbations to the wider scale displacements of well, we could base our enrichment on that, and so this is very similar to XFEM. Back in the early days of XFEM, what they said was you can take your conventional description, but also add something else. So these are our enrichment functions. Well, in this case, we still have our shape functions, conventional polynomial shape functions. Then we have our enrichments, these psi's, sub L, and then that combined function is multiplied by an amplitude, capital B, and that amplitude becomes one of our unknowns that we have to solve, just like we have to solve these known displacements here. And the enrichment functions come directly from that Williams expansion, and they look like that. So building that into, oh gosh, this is a bit scary. Building that into our subsequent into our integral equation, boundary integral equation, we end up with something that looks like this. Let's not worry too much about it, but essentially this gives you matrix terms here based on boundary integrals. You have the conventional boundary integral here, and then you have the enrichment ones here with the enrichment function. And then you can solve that linear system. You get your nodal coefficients uj. I hesitate to call them nodal displacements because you've added something else in here, so it's not quite the same thing. You get your b's, and at any location, then you can recombine these to recover your displacements.
Do you have to be able to do those intervals analytically?
No. Mostly they're done numerically. Now, so if you've got your displacements, you can get your strains and stresses internally as well, and there's a J integral approach some of you may have come across, which says I'm going to take my crack tip and I'm going to integrate on some contour, let's call it gamma J integral contour. There's a function now, I'm not going to show what it is, but it's a conventional way of integrating an integrand which has to do with the stresses, displacements, and the work and energy and so on. And you recover those stress intensity factors, and so this is, I suppose, the earliest one that we came up with. Number of degrees of freedom, error in K1, and this is a very simple case we're looking at, and look at the benefit you get for just adding in a small number of degrees of freedom. Boom, you're reducing your errors by order of magnitude.
Is that B in the amplitude field, is that a two-dimensional field of R and theta dependency, or is that just...
Good question. Good question. Yes, it has R and theta dependence. Now, the interesting thing is that if I'm going to apply that, I'm going to integrate those things over the element on the top and the element on the bottom. Theta is a constant here, theta is a constant here. So we're only taking in our implementation of the EM, only taking a slice through constant theta sections through that R theta variation. But embedded in that is the behavior. Anyhow, so like I said, I'm going to go into the fracture mechanics in more detail. So really, basically what we've done is reach where we were last time I was here in this room. So apologies to those of you who were here last time I was here in this room. I guess you think I've been sitting with my feet up for the last 9 years. There's more things that I'd like to show you when we get on with the application.
John, I know the remark this in 9 years back, still remark all the thing. So this whole procedure works with asymptotic representation only in 3D. So there is no such analytical representation available.
No, well, we have got some 3D solutions, so we can take plane strain solutions around a crack front along slices.
Not on the edges.
Not on the edges.
That's
pretty good. Okay, so let's go on to FEM for heat transfer. So this is something which is definitely post 2009 when I was here last. So simple problem solving the heat equation here. So we've got a time dependency, spatial dependency, and some source term. And we have some very general way of casting out boundary conditions here in space and time, and some initial conditions spatially. So a very standard setup of a problem, and a standard approach to now discretizing time first. So we'll use a very simple linear time discretization, rearrangement, and then we take from this form, we integrate it with a weighting function in a classical way, and we end up with a weak form. So it's like this. So this is the weak form that we're working with. So nothing different there from classical finite element solution to this problem. Our unknown is u at the time step n plus 1. And so the question is how we're going to enrich that. Our first thought about this is one of those ones where we're taking the enrichment function from our own engineering interpretations. And, in engineering, you get used to running simulations quite a lot. And you get to see the sort of stress behavior, acoustics behavior, thermal behavior, what those distributions look like. And very often when you have some sort of thermal source that's going on, if you plot the temperature as it goes past that, as you go from far field to the source and pass it through to the far field the other side, but you could do it. It goes up and it comes down. What looks like that? It's a Gaussian. So we thought, let's try some Gaussians. There's nothing in the equations which say that the Gaussian is the right solution for this. But we're going to try some Gaussians and see what we do. So for these problems where we have some sort of single or multiple sources, we have single or multiple Gaussians with which we might enrich. So let's express our temperature in this case, U. Okay, so we have an H there for the finite element discretization level. N, I think, is just the element it's on, forgive me. So we get our shape function again. Then we have the enrichment function as a capital G, and then the B becomes the amplitude that's finds its way into the solution vector. So that becomes our unknown. So the enrichment function would be a standard Gaussian function with some spread, some Gaussian parameters. And so here's a picture. Maybe it's the angle we're looking at here. So this is what my student gave me. They don't look very much like Gaussians to me, but it shows me they are. Anyway.
So these are centered at the node points?
This is centered at the source, where you've got a thermal source.
Okay, so node is not the plane.
It's not.
Is it possible the z-axis is log?
Well, I can see very closely. I've got a 0, I've got a 0.5, and a 1, so it doesn't look like it just from that perspective. Anyway, regardless of the veracity of the plots, you can imagine there is a Gaussian function which is quite steep, like this over the source, and with a different set of parameters, you might get a very diffuse flat, and you get a whole family of the middle.
So could you say again what R naught and RC are?
It's
So you have a source somewhere in the domain.
Yeah.
So R naught is the distance from the source.
Let me talk to you later about it. I'll go
Okay, all right.
figure it out. But, anyway, the
I think
basic-
probably some of us are thinking radial basis functions.
Yeah.
We're crazy about radial basis functions.
Oh, Gauss, I mean, this
So,
is,
but
this is essentially
there the location would be, you move them around. So, but I think you're putting them in a physical location.
we're putting them in a physical.
Thank you.
So, I mean, the idea then is that, when you switch your source on, immediately you get a spike. It's a very localized spike. It hasn't reached the far field yet. You get that sort of behavior. So, in your solution vector, the amplitude for that one becomes quite large. The amplitude for that one, very small. Time passes, and the temperature field itself does become more diffuse. And as those time steps go on, you see the amplitudes of the steep one decreasing and the flatter one starting to increase. So very interesting to see the behavior there. This is just a simple example. I mean, it's not that, it's quite nasty. You've got things to the power of 20 going on there. However, basically that is just a problem which is, as I described, it's one source in the middle, it starts out like this and then diffuses. And, well, here we're using 6 Gaussians to capture this. And the nice thing about having 6 at the same time is they're all in the same matrix. It's all built into your linear system. So at no stage do you have to recalculate a new system matrix. It's all in there for every time step.
A little bit denser than standard fundamentals.
Denser than standard fundamentals. But the benefit is that you have a much smaller number of elements.
So each element has 6 additional Gaussians enriching it,
Yes.
or there's 6 global Gaussians? Okay.
There are 6 global Gaussians, but each element has, at its node, has its own amplitude, which says how much that basis function's amplitude amplified. So anyway, if you look at different behavior as the time steps pass, very nice behavior showing the results converging, but also I think there's evidence to say the convergence rate is the same, but with this delta of again approximately 1 order of magnitude.
So you are labeling partition affinity.
Why?
Yeah, because it's more of an enriching as opposed to partition affinity. Partition affinity, that structure, are you putting in that structure there, partition?
It has a partition unity structure. If I go back here, I interpret partition unity by the fact that I've got this shape function. That provides a partition.
Okay.
It's my interpretation.
For engineer, you can do anything you want.
Okay, so here's another example. We've got 4 sources. You can see that they are varying strengths here, so some are stronger than others, causing more perturbation to the temperature. These are switched on at time 0, then they're turned off at time t equals 5 seconds. And you can see that the patterns that after 10 seconds, after they're all switched off, become this much more diffuse distribution.
So you haven't shown the source at all, right? You showed the solution.
Yeah.
So the source is what? That's what
There's one
also
here,
seems
there's one
sense.
here. You can see actually probably see little squares in there. That may be evident in the other pictures, and they're all in the same places.
Okay.
To be honest, I haven't got here the data which says what are those source strengths, but you can see the relative magnitude.
Okay, so you chose the source of this impact from this right hand side of the field equation.
Yes.
Here. And it is pretty mild in other places. Okay.
I was just curious, for the 6 Gaussians, how do you know how to order them in terms of like which one goes on which term and how sensitive is it?
All nodes have all of them.
No, but in your sum, you sum over the 6 Gaussians, so each one is multiplying a different term, right? So in terms of, if all of the 6 Gaussians are each different, how do you know which one goes on which of the 6 terms? Does that make sense? They're 6 distinct Gaussians, correct?
Yeah. So every node has its temperature expressed in this way. So really, for each node, there's going to be 6 degrees of freedom.
Okay.
I can answer it. So the shape functions take care of that. Because you know what, shape functions kind of survive only here. So if it survives only here, it doesn't see other Gaussians. So there's no need. The ordering is done by the shape functions. So the shape functions doesn't look at the other Gaussians because it's zero there.
Right, but it's a sum of, I'm thinking of it as like linear combination where these are the coefficients. So how do you know which one goes on which term? But maybe I'm just not saying
Well,
it correctly.
that's what comes out in the wash when you solve the equations. Because those coefficients are your solution. When you solve your AX equals B, your linear system, what sits in X are the coefficients that multiply.
And is it really sensitive to your choice of the Gaussians?
Yeah, and obviously you've got to choose some Gaussians which look like the solution. So you've got to be a little bit careful which ones you choose. You know, if you choose a lot of one, if you choose 6 of them, then they're all
Right.
like that, but just small differences, then they're not going to be very good at capturing the more diffuse ones. So you've got to choose a range which will be active over the duration of the solution. A good question, how you choose your enrichment. So anyway, I'm going to take a line across here from left to right and look at the difference. So we've got these 3 different meshes. This is our reference mesh. We're assuming this is going to give us our reference solution. This is a moderate finite element mesh. I'm going to compare this against this. And because of this factor of 6, broadly speaking, they're about the same number of degrees of freedom. Those two other cases.
Has anybody done analysis for this? Do you know, Marcus? Nobody has done it. I don't see this method as option.
I don't think so.
It just works, yeah.
You're engineers. So it's a bit of a clunky display, I'm sorry about that, but basically these are the errors at the top, that sort of moderate finite element mesh, and here the errors on the same scale from the enrichment. You can see all the scales are the same, top and bottom. So you can see the enrichment is doing a great job at half a second, another great job at 5 seconds. Out at 10 seconds, it's good, it's better than this one, I'd say, but it's not that much better. And the reason is that at 10 seconds, that's what you're trying to capture. And the polynomials are able to do a great job of that. So you would expect the enrichment not to give you a great benefit. Then we looked at problems which said, okay, maybe we've got some piece of glass. We think about glass. And it's in an oven during the manufacturing process. You take it out of the oven at time t equals 0. What happens then? And it's in those early time steps that in the boundary layers, you get cooling at the boundary initially. And in those early time steps, you get some very steep thermal gradients, and those have influence on the structural integrity of the glass. Which is why we do careful annealing of glass and cool it down slowly. But we thought, let's model what was going on there. And at the boundary layer, you're going to get, if we were to plot x is our distance from the boundary, x equals 0 lies at the boundary, we've got temperature, we might expect to see something that looks like that. And then a little bit later, we might expect to see something that looks like that, and so on. And ultimately, we would see something that looks diffuse. So we thought, well, I don't have a different coloured chalk, but going back to our initial work with trigonometric and hyperbolic functions. So if we work with a hyperbolic function, hyperbolic tangent, it kind of looks right. Let's explore the use of hyperbolic tangents. So this is a family of hyperbolic tangent. This is how they might be expressed on a square domain. It's that sort of shape up the sides, flattening off at the top, with different gradients, depending on, sorry, I don't have the equation here for it, but it's a tangent, depending on this value k.
Is a tensor product of hyperbolics? In the basis?
In this case, it is, I think, the addition of 2. The addition of one that goes like that in x, the same thing in y. But it's a global function. Now, in this case, we're applying it. Maybe your parents had the same sort of cake tins as my mum had. Like the ring ones, the ring cake tins. And if you sort of invert that, you would get what the enrichment function for this is. So hyperbolic tangent then flattens off and then down the other side in an annular fashion. So, well, I'm not going to dwell on the physical example here too much. But again, we've got a sort of reference finite element mesh here, a sort of moderate finite element mesh here, and this is our extremely coarse partition beauty finite element mesh for the enriched solution. And we've got 5 of those hyperbolic tangent functions. We're not using any of the Gaussians. This Q is the number of Gaussians. That's the number of tangents. And we're just expressing the differences just very qualitatively, eyeball norm, as we might call it, after 10 time steps, 50 time steps of what the temperature distributions, what they look like. And really, they all look pretty good. But this sort of moderate finite element mesh, you're getting these rather spurious oscillations in the solution. And if you're going to use those to calculate those local steep temperature gradients, which is an engineer going to be interested in, then you might have I'm going to gloss over those ones because time is way too short and go over onto the compounds problems. Now, I did describe some of this back in 2009. There are many other methods where the enrichments are used. This is by no means the only approach, but we will describe this plane wave enriched boundary element for wave scattering. So let's not even go through those. But other methods are available. So, solving a Helmholtz equation could be 2D, 3D. I think my examples are 2D, but we've done all these in 3D. We've got an incident wave, which is just a plane wave of unit amplitude, and we have some sort of condition, what is condition, or in fact, most of our problems you look at sound hard conditions, but it's an expression of alpha and beta both being 0. Similar looking boundary integral equation as we had before, which provides the boundary element method, dealing with phi as the potential, which can figure the wave height above the mean. Again, we've got a Green's function, G, a fundamental solution, its derivative, and so on. And we've got the incident waves at the other end. And this is where we go back to our limitation of number of nodes per wavelength.
So you are using combined field.
We're not using it both.
Okay. Reason is it's comfort. You don't want
It's easier to use chief and it worked.
All right.
So, this is a case where we would say, okay, well, plane waves are complete with Helmholtz solution. Let's express our solution in terms of, here's our shape functions again, here's our amplitudes, and now we have a set of plane waves, each going off in some direction dm. That's a unit vector in the direction of creation of the plane waves. So, in this case, just showing very diagrammatically, it's not really a very good description of it, but we have 8 plane waves of this node going off in the 8 different directions. And so what we're aiming for then is a description of the potential over this wave solution, this auxiliary solution over this space, which is given as this sort of weighted linear combination of those plane waves. And the great thing you get out of this is because you're building the oscillatory nature into the element, you're no longer governed by that. I've rubbed it off now, but we have 10 nodes per wavelength. We can have one element with 50 wavelengths. Great. So, although every node has many more degrees of freedom than it did before, in this case, every node had 8 degrees of freedom. I could choose a different number. So that quadratic element might have 24 degrees of freedom, whereas with a conventional Lagrangian shape function, you have 3 degrees of freedom. But you're using far fewer elements. So where's that trade-off? There's a trade-off. How's that balance work? These are our initial results from many, many years ago. Scattering from a cylinder, happily we have an analytical solution for this, and we solved this with 192 degrees of freedom. That can either be 192 standard boundary element nodes, or you can accumulate your degrees of freedom by having more elements and fewer plane waves, or more plane waves and fewer elements. And you get various different behaviors. What turns out to be good Well, they all turn out to be good, much better than the unenriched. But the ones that are really good are down here, these triangles. These are the ones, in the extreme case, 2 nodes, end node, mid node, end node, 1 element, with 96 plane waves. So it takes you back to not to the boundary element method, the original incarnation to the boundary integral equation. And the nice thing is that it reduces, instead of that 8 or 10 per wavelength, we can get away with 2 to 3. So some issues to do with that. There are more degrees of freedom per element now than just the number of nodes. So if you just collocate at the nodes, you're not going to have enough equations. You're not going to have a square system. So you need to collocate at more places. Anywhere on the boundary will do just equal to space. We need some strategy to deal with a non-unique solution, which is what Dinesh's question was about a moment ago. You can either, there's 2 main approaches. One is the quick and dirty approach, which is what we use for Chief. You just place some points, collocation points inside the scatterer, or you go to a confined field into an equation, but Burton-Miller off the ball. We like Chief because Burton-Miller will incur more integration costs. This is integration heavy in the runtime analysis. The other thing is we need to evaluate some highly oscillatory integrals now, because our elements span many, many wavelengths. The things we're integrating are highly oscillatory over the element, and that's nasty. The other thing we need to take care of is the condition of the system. In any paper you read about enriched methods, you always see something about conditioning, because it does degrade the conditioning, and that causes some difficulties. You have to be aware of it. Here's the interesting thing. The more plane waves you throw in, the worse your conditioning becomes. And that's a natural thing to expect. One of the reasons you might get ill conditioning is if 2 of your basis functions look the same as each other, or very similar to each other. Very difficult to find the right balance between those 2. If we've got 96 plane waves, as we have the worst of those cases, the most extreme cases, those 2 plane waves are propagating in a very similar direction, so the conditioning does degrade. However, as we've seen in that graph, you get the best results, because that is a very rich approximation space to capture the solution. So if your solver can cope with the conditioning, that's good. It does mean that when we do some of these simulations, we have to use quite an expensive solver. We use SVD, so you add in decomposition and truncate that, and that gives us a good solution. If you go to 3D, things tend to be a bit better. 3D and 2D. Now that may be to do with the fact that you've got another dimension, so that angle between those two vectors, there's another dimension which may help to separate them. But it's also, I think, to do with the fact that your Green's function decays in 3 dimensions rather than 2 dimensions, which would suggest that your matrix is more diagonally dominant. However, you can manage the yield condition by controlling this thing, the degrees of freedom per wavelength. The thing which might be 8 or 10, I was talking about before. I was saying you can get away with 2 or 3, great. If you were to choose with the enriched methods 5, 6, 8, 10, the conditioning would be through the roof. It would be very difficult to use.
So you use the same direction for all nodes, correct? I mean, so you choose 8 nodes, so do you do it like a North Pole, South Pole, to the equator? I mean, what do you do? I mean, is it automated for you?
It's automated. We use the incident wave because in high frequency asymptotic behavior is that you can express the displacement as a slowly varying function times the incident wave, whereas it's 2 times the incident wave on the illuminated surface and 0 shallow.
Okay,
so we always include the illuminated, so the incident direction, then we just increase space.
From there, okay.
But there's a lot of research to be done about, is there a better way of doing it? In my experience, I've tried a few things. In my experience, it's the number of waves you have rather than their directions.
Because one of the ideas was you can control the conditioning by choosing the right number of points on the sphere, which is the direction. I mean, it just boils down to choosing points on the sphere.
Yeah.
And there are some research there. So that was a while back, I think I'd love to be there.
Well, I'll talk to you about that, because this is something I'm going to show now, which is how we might describe those directions. So this is simple in 2D, just equally spaced. In 3D, it's like points on a sphere. You'll stand in the center of a sphere and you're looking at points. Those give you the directions. So one thing you could use is this discretized cube. Just that gives you 8 directions. If you have finer discretization, you've got 26, 56, 98. This is limited, of course, to the discretization, the equal discretizations in the cube, n cubed minus n minus 2 cubed. And that gives you a set of directions, but they're okay. Yeah, they work all right, apart from that limitation on the restriction on the m that you can choose. There's a little bit of a non-uniformity in the space. So we tried something different, which is just treating all of these as particles on a spherical surface, and they've all got some charge. They repel each other with the Coulomb repulsive force. And we just set up a tiny little, very simple time-stepping scheme to find their equilibrium. This is my artificial animation, and they very quickly come to a nice distribution for arbitrary m. So that works great. It works in a blink of an eye. So the integration of the oscillatory functions is something else we've been looking at in the intervening period. These are typical integrals over a line element for a 2D simulation or over a quadrilateral element for a 3D simulation. And these are the sort of integrals you have to take care of. So we've tried all sorts of exotic things, including, basically, you could use a bucket full of Gauss points. A zillion Gauss points, that's why it's integration heavy.
Is there a technique called Phelon integration?
If you wait for about 2 slides.
I did that in undergraduate.
Okay.
Sorry.
So another method we've tried, steepest descent, where there is a path which goes from here to here. It's not this one in the black line, which the integrand is non-oscillatory. That's the one which goes into the complex plane and out to infinity along a bit and back down to here, as long as you can find that path. So that's an interesting way. We've tried all sorts of things, and they all work for individual cases very, very well, but none of them we've found works across the board for the hundreds of thousands of cases that you're going to get when you do a typical simulation. So we've been looking at a Phelon method. So here's Graham's method. So you've got something slowly varying times something rapidly varying. And the idea then is to express the slowly varying thing in terms of a polynomial. It's important to use a Hermite polynomial to get conditions at the end right, the gradients at the ends are correct. And if you've got a simple form of G, it's very straightforward. We have a slightly more complicated form of G, so we would go through this coordinate transformation first to put it to get the simplest form. So ID, IKG, and you've got DG over here, so that's nice for us. And it incurs this d psi dg Jacobian term as well. So the idea is you approximate this product f times d psi dg, this Hermite polynomial, that gives you polynomial coefficients. You can calculate these moments. This is done by parts analytically, and you just assemble it all together. It works beautifully. Alternatively, there's the asymptotic method. So this is just taking this slowly varying f psi times the rapidly varying exponential, a little bit of rewriting of that very simply in the first place into a form you can easily take it by parts, and that gives you this first order approximation here based in terms of just the endpoints. And here's the error term sitting on the end. Now you can then do it again if you want. Take that by parts, you get another term based on what's happening at the end points of your interval A and B, and some other error term there. And every time you do this, we're dividing by k, and we're looking at large k simulations. So this is rapidly converging.
You need to know the
I did
moment.
this in class this week.
It's Calvin's
It's the method of stationary phase. Is that what you were going to?
I'm not going there.
That's right.
Some students in my class.
So you need
I'm getting excited.
So that's what I mean. You're not using any stationary points at all, right? Also, your moments are no. Your moments are exactly. I mean, that's a finite weakness, right?
The problem is the stationary points.
Right.
Okay. Before we get to the stationary points, Okay, so this is the errors you get with the asymptotic method. You take it once, you take it twice over a frequency range. You see things get better as the frequency goes up, which is typical of these methods for highly subfrequent. Anyway, we just compared these various different methods. Basically, this is kind of like the time it takes to generate a graph that looks like this. So that's what my students selected, and you can see that with Gauss-Lejeune, the time increases, the line decay for a manageable, controllable error. With Phelon asymptotic, you see the error is decreasing with broadly constant runtime, so very nice. Now, with the stationary point case, so stationary points are where dg dxi goes to 0. And it looks a bit like that visually. So you lose the oscillation over a period of a portion of your interval. We haven't found a way of getting the asymptotic scheme right, but I'm happy to talk to you. I'm very glad I'm here. We have found a way of doing it with Phelon that you end up having to evaluate some transcendental functions to do that, the error function. But it's expressible in terms of the error function, that's fast. The difficulty with all these methods is that you get these pathological cases. Here's your element here, and you've got a stationary point just outside. How do you identify that? How do you deal with that? And that's where we are at the moment, trying to deal with those pathological cases.
And then you get this F with the singularities, right? What do you do with that? No, that's singularities, you're not even thinking about it.
We're not thinking about that. These are for the regular integrals. However, when you do this transformation for Phelon to take account of the stationary point, that gives you a singularity. So I think it's probably going to look very much the same as that.
Okay, so
I think
that's our point, right? So you have a similarity there.
I mean, basically, it takes the stationary point case and converts it into a case which doesn't have stationary points, but which has a singularity in the outside chain.
Some years back we found for this 3D problems, stationary points are not sufficient. So we did when you go to the secondary order, this is the whatever the steepest point or something like that. And I'll talk about it for that.
That'd be interesting. Anyway, finally, I realise I'm running out of time. It's nearly 5:02, so I apologise for the overrunning. Finally, just something that we've done in the last small number of weeks is thinking about, well, can we enrich the corners, so the scattering from corners? This has been done in other numerical methods. We thought we'd try with plane wave enriched BEM or just BEM as well. We know that we can express this asymptotic behavior into the corner in this fashion here. You've got a Bessel function of Kr times a trigonometric function, and so alpha is defined by the exterior angle. So we can have, well, this is our standard plane wave enriched. You could have the conventional BEM there, plus this other thing. Here's your enrichment function, which comes from the asymptotic behavior times its amplitude. That amplitude ends up in your solutions that you're going to solve for it. So we have for just a square scatter, a very simple case. Again, the error against degrees of freedom. And we can see a straight BEM. Down here is the best one, which is the plane wave enriched with the extra Bessel functions and corners. This is the BEM with the Bessel functions and corners. And this other interesting one here is just replacing that Bessel function, this here, with just the very basic asymptotic low argument behavior, low R behavior, which is R to the minus alpha. So we just throw that in and see how that performs. It's better than not doing it. It's not as good as having a full Bessel function. Anyway, I've reached the end. It's kind of interesting to do, just throwing things which are not polynomial. We have some fun with that and deciding how we can do it. You've got to choose your enrichment functions carefully, so good question. You've got to integrate these carefully. Careful integration is really important because this is an ill-conditioned system. And if you're making integration errors and it's ill-conditioned, those errors can expand and blow up in this solution. But ultimately, what we're looking for as engineers is accurate solutions from coarse meshes, whether it's BEM or FEM. in a way, it doesn't matter. We've got to watch for conditioning. It does get worse. The more enrichment you throw in, the worse the conditioning becomes. We've got 3 different applications. I should acknowledge the people that really did the work. I just sat in my office and saw them every week or two. If you're around November 14th, it'd be great to see you again for the fracture mechanics in a little bit more details. But thanks for coming. That's the opportunity to speak.
Right. Here you go.